We throw around the word same all the time, right? Hey, we have the same shirt, or these two coffees taste the same. It feels simple. But what if I told you that the entire idea of sameness is kind of a logical illusion, a mental shortcut that, believe it or not, leads to some of the biggest, most mind-bending paradoxes in all of philosophy? Let's dive into the logic of abstractions. So, that's the big question we're tackling today. What does it actually mean for two things to be the same? Is it some hard, fixed fact about the universe? Or is it something our minds just kind of make up? And right away, we run into a huge problem. See, you've got two completely different kinds of sameness. In the perfect, clean world of mathematics, identity is absolute. Two is two, a circle is a circle. End of story. But then you step into our messy, physical world, and suddenly nothing is ever truly identical. I mean, if you zoom in far enough on these two identical grains of sand, you'd find billions, trillions of differences. This huge gap between the ideal and the real, it's a massive problem for classical logic. To really get this, we've got to look at how old-school classical logic tries to handle identity. The best way to picture it is to imagine you're trying to define something with an infinitely sharp, perfect needle, just perfectly precise. Yeah, this needlepoint idea has a fancy name, punctiform meaning. Punctiform just means point-like. It's this assumption that an object's identity is an exact, single, infinitesimally small point. And for our brains to even pull this off, we have to do a couple of amazing mental tricks. First, we have to mentally draw a line around an object, separating it from everything else. Then we have to just assume it doesn't change from one moment to the next. And here's the real kicker, and this comes straight from the source material. This idea of perfect sameness, it's not actually out there in the world. Nope, it's something our brains literally invent. We perform a mental act, this abstraction of identification, to create the very idea of identity in the first place. It's a creative act. And this whole mental shortcut is so fundamental, it's been boiled down into three super simple, elegant rules, the axioms of equality. You've got reflexivity, A equals A, duh, right? Symmetry, if A equals B, then B equals A, makes sense. And then the big one for us, transitivity. If A equals B and B equals C, then A has to equal C. Seems like a rock-solid system, doesn't it? Well, about that rock-solid part, this is exactly where that beautiful, clean logic just completely faceplants into the messiness of the real world. This is the world of indiscernibility, where things aren't perfectly identical, they're just, close enough. So what happens to those neat little logical rules when things are just close enough? When our eyes can't tell the difference, or our fancy instruments have a little bit of wiggle room in their measurements? Let's find out. All right, let's put this to the test. Imagine we have three color swatches. We look at swatch A and swatch B. To our eyes, they are absolutely indistinguishable. For all practical purposes, they're the same. Okay, now we look at swatch B and swatch C. And again, they look exactly the same. So far, so good. Logic tells us exactly what should happen next, right? A equals B, B equals C, so... But nope, put A and C next to each other, and you can totally see the difference. Our third axiom, transitivity, has just completely broken down. The whole logical change is snapped. This is a classic example of something called the Sorites paradox. It's all about how you can't pinpoint the exact grain of sand that turns not a heap into a heap. And it's the perfect showcase for why pure, perfect logic just struggles with the real world. Okay, so if the old logic is broken, how do we fix it? How do we build a logic that can actually handle reality? Well, the solution's actually pretty brilliant. We just have to stop thinking about that infinitely sharp needle and start thinking about the dartboard instead. And this quote really nails it. The goal isn't trying to hit some impossibly tiny target with a perfect needle. The real goal is defining how big the target area, the dartboard itself, is allowed to be. We get to set an acceptable range for what counts as the same based on what we need. And this idea is called interval meaning. So instead of a perfect little point, sameness becomes a range, an interval, a margin of error we can call epsilon. And anything that falls inside that predefined range, we just agree to treat it as the same for whatever we're doing. It's super practical, whether we're in science, engineering, or just, looking at colors. You see how this totally changes the game, right? In classical logic, that chain of transitivity is supposed to be unbreakable. It goes on forever. But with this logic of abstractions, we get something called K-transitivity. It basically means the chain of sameness can only stretch so far before all those tiny little differences add up and snap, the chain breaks. Now, I know what you might be thinking. This sounds like a neat little philosophical mind game, right? But this is a huge deal. Recognizing these intervals helps us crack some of the most famous, most stubborn puzzles in the history of logic and mathematics. I mean, for 100 years, problems like these threw the foundations of math into chaos. You had stuff like Russell's paradox, this total head-scratcher about the set of all sets that don't contain themselves. Then you had Poincaré's jump, which asked, how on earth do scientists justify leaping from a bunch of messy, real-world data points to one single perfect equation? And the solution, according to the source material, is staring us right in the face. These paradoxes aren't really paradoxes. They're what happens when we forget what we did in the first place. We use a fuzzy interval to create a concept, but then we turn around and treat that concept like it's a perfect absolute point. We completely ignore the mental leap that got us there. Yeah, this table lays it all out pretty clearly. For Russell's paradox, the contradiction just vanishes when you remember the abstract interval you used to define the set to begin with. And for Poincaré's jump, that leap from messy data to a clean theory isn't a flaw in the process, it is the process. It's the necessary jump from a real-world interval of measurement to an idealized, theoretical point. So what this really does is completely upend how we think about logic itself. It stops being this rigid black and white system of absolute truth, and instead it becomes this amazing spectrum, a whole rainbow of colored logics, each one custom-built with its own interval, designed to perfectly connect our abstract thoughts with the world we actually live in. All right, so let's boil this all down. What are the big takeaways? First, perfect absolute identity. It's a mental tool, a really useful one, but it's not a real feature of the universe. Second, a much more practical way to think is indiscernibility, things being close enough within a certain range. Third, this whole interval concept is the secret bridge connecting our abstract ideas to messy reality. And finally, number 4, understanding this is how we solve those ancient mind-bending paradoxes. It's all about defining our terms. And that leaves us with one last big question to think about. If something as rock solid as formal logic actually depends on these flexible, human-defined boundaries, what else are we so sure about? Which of our other absolute truths, in science and ethics, even in how we see ourselves, are really just well-defined intervals that we've just forgotten that we drew the lines for?